Let us briefly review what we discussed in the previous class, and then I will move forward with the new content today. Turn off your mobiles and keep the mobiles in your pockets throughout the class. In the previous class, we took some definitions. We started with the definition of a random experiment. We said any experiment that has the capacity to produce different outcomes when repeated under the same conditions is called a random experiment. You have an experiment, you repeat it again and again under the same conditions, and the experiment can give you different outcomes. It's a random experiment. If you list down all the outcomes of a random experiment, that's a sample space. If you take a subset of that sample space, that's called event. So this is the summary of this whole slide. We discussed many examples of random experiment, then we made their sample space, and then we defined event out of them. Then we defined formally what is a definition. Few things you need to keep in mind throughout the course. Number one, probability is a number. It's a number. We might give you in exam a question that what is the probability of this event, and the options are 0, phi, and others. Phi is not the probability. Phi is a set. Probability will corresponding to phi will be 0. So the correct answer should be 0, not phi. Phi is not a number. Phi is a set. Probability cannot be a set. Probability is a number. Number one. Number two, we said probability is a number between 0 and 1. So keep in mind, if you see any option which is less than 0 or greater than 1, immediately discard it and think about the remaining options. We took an example how to find the probability in case we roll a fair die. We rolled a fair die. We said the sample space consists of 6 outcomes, 1, 2, 3, 4, 5, 6. We defined event A that the number which comes on top is greater than 2. Then we wrote down A in terms of a set. It was 2, 3, 4, 5, 6, 3, 4, 5, 6. We counted the number of outcomes in event. We counted the number of outcomes in sample space. We put them into the ratio formation of probability, and the answer was 66.67%. Then we talked about the complement theorem. We said that the probability of complement of an event is equal to 1 minus probability of the actual event. Now, what is the identity behind this result? The identity behind this result is that A complement is equal to S minus A. Like I said, phi is a set, 0 is corresponding to phi. 1 minus A complement, probability of A complement is the result. Behind the result, this is the equation that A complement is actually the part of sample space that does not belong to A. On the right side here, I'm talking about this diagram. What is the A complement? The blue part. And the blue part is actually S minus A. It's the part of sample space when I subtract A, right? So it's actually S minus A. Then we talked about the addition theorem. The addition theorem says that the probability of union of two events is equal to probability of A plus probability of B minus probability of A intersection B. We briefly discussed what was in the background of this theorem, which is not a part of this course, but for your understanding, we discussed how this theorem comes and what is in the background of this theorem. But from your course point of view, you will be given this equation in the blue color at the top. You will be given this equation in the formula sheet. So you just have to apply this equation on the problem. There might be, there are some questions in the exercise that I saw related to 3 events, union of 3 events. So you might be asked to use the addition theorem for 3 events. Now, today we will discuss some of these definitions that sometimes we have to give you some extra information, but we don't give you that extra information directly. We give you in terms of these terminologies. I will show you how. The first terminology that you need to know is, when do you call the 2 events to be mutually exclusive? Read the definition and you will see the 2 events are called mutually exclusive if their intersection is phi. If they cannot occur together. For example, I roll a die Event A is that I get an even number. B is I get an odd number. Can I have a number that is even and odd at the same time? So I cannot perform the experiment and the outcome satisfies both event A and B. Here you can say A and B are mutually exclusive. Okay. Similarly, if I define event A to be that the number is less than 2 and B is that the number is greater than 4, these two events are mutually exclusive. There cannot be a number which is less than 2 and at the same time greater than 4, right? So two events or even more than two events, they are said to be mutually exclusive if their intersection is phi. And when the intersection is phi, what would that mean? That the probability of their intersection is 0, which means that the addition theorem that you took in the previous slide here, it will be limited to probability of A union B equals simply probability of A plus probability of B. Now we might give you a question in exam where we don't give you the intersection probability. We ask you to find the probability of A union B. We give you probability of A, we give you probability of B, but we don't give you A intersection B. But we tell you that they are mutually exclusive. So we are giving you the A intersection B indirectly. Indirectly, we are telling you it is 0. Right? So you just need to know these terminologies. Why? Because in some questions, the information is given in terms of these terminologies indirectly. So you need to use that information to solve the question. The second definition that we use is exhaustive events, collectively exhaustive events. Two or more than two events are called exhaustive events if you take the union of them and you get the whole space. In the second diagram, if I join A and B, what do I get? The whole space. So if you have two or more than two events, here, like in this example, I have this and this. This is, let's say, E1, this is E2, and this is E3. Here, E1, E2, and E3 are collectively exhaustive events. Why? Because if I join them together, what do I get? The whole space. So two or more than two events, they are collectively exhaustive if the union covers the entire sample space. This means at least one of them must occur. For example, if I roll a die, event A is that I get an even number, B is I get an odd number. Now, when I roll the die, each time, either A will happen or B will happen. I cannot have an outcome which does not belong to both of them. So A and B collectively, they cover the whole sample space in this case. And then finally, the De Morgan's law. Let me confirm if this De Morgan's law is given in your formula sheet or not. I think it should be given. No, it is not given, which means you need to remember the De Morgan's law. The De Morgan's law says, the De Morgan law says that the probability of A union B whole complement is equal to probability of A complement intersection B complement. And A intersection B whole complement is equal to A complement union B complement. You take it in what, high school or what? The De Morgan's law. It is covered somewhere. Somewhere it is covered. Just try to understand this De Morgan's law using the Venn diagram. I will explain one of them using the Venn diagram. Suppose you have this as a sample space, and this is event A, and this is event B. Okay, let's come from the left side. The left side of the first one is A union B whole complement. So let me first highlight A union B. This is my A union B. Correct? What is A union B whole complement? Everything outside the yellow space, but inside the space. That's the left side. Okay. So let me write here. This is all A union B whole complement. Clear? Everything outside the yellow. Now come from the right side. Here I will make that. A, B. The right side says A complement intersection B complement. Okay, so I will highlight A complement with the yellow color. A complement with the yellow color. So I will highlight everything outside A. Correct? And I will highlight the B complement using blue color. So everything outside B. And what am I interested in? The intersection of the two. I have A complement in yellow color, B complement in blue color, and I'm interested in common area between the two. Now, what happens when you join blue and yellow? The common area becomes green. Do you see that this common area, green area, is the same as the white area on the left diagram, which shows that A union B whole complement is actually A complement intersection B complement. And you can perform a similar activity for the second part of De Morgan's law, which says that A intersection B whole complement is equal to A complement union B complement. Now we will make use of all of these concepts to solve this one comprehensive example that I created. I will use this example to elaborate the concept of probability, the concept of complement, the concept of union, the concept of intersection, the concept of mutually exclusiveness, the concept of De Morgan's law. All of them I will implement using this example. Last row, is the font size okay? Okay. So let's say the question says that we have a batch of students at KFUPM that has a total of 500 students. I will highlight the important pieces of information from this statement. I have a total of 500 students in my space. Out of these 500 students, how many they belong to the MUM? 150 are from the MUM. How many from Riyadh? 100 from Riyadh. How many from other cities? 250 from other cities. Good. This is one way of categorization. And you see this information here. I have a total of 500, 150 from the MUM, 100 from Riyadh, and remaining 250 from other cities. What if this statement was, this part of the statement was not given? You can get it from the remaining numbers, right? If there are 150 from the MUM, 100 from Riyadh, of course, the remaining are from other cities. Out of these 500 students, now the further pieces of information say out of these 500 students, there are 50 that belong to business departments. And the rest of 450 belong to engineering department. So here is that information. The total number of business students is 50 and the total number of engineering students is 450. Further, there are 15 business students that are from the MUM and 15 students, business students that are from Riyadh. So this 15 is what? This 15 is now intersection between the MUM and business. We said 15 students are business and they are from the MUM. And there are 15 students who are business and they are from Riyadh. So we get these two numbers, 15 and 50. Now the first task is to complete the table. can you complete the table? Always there will be a minimum amount of information required to complete the table. For example, if I only tell you that there are total 500 students, can you complete the table? You can't. You need at least a minimum amount of information to complete the table. And I think this is the minimum amount of information. I can leave like 4 to 5 cells to you. You can complete that. But the remaining information I will give you in the question. Now, how do we complete this table? Yes, if I don't give you 500, you can know the total. The way I said, if I don't give you 250, you can get the 250.
He give me the number of students.
If I don't give you this, then you can find this from 500.
Yeah.
Yes. But anyhow, for this question, how do we fill the table? How many students are from the mom? Yes. Good. Somebody else. For Riyadh, okay. 85. Somebody else. Where? Here? What's the reason behind 20? 20. Yes.
230.
Why?
Because the remaining is out of 450 minus the total.
Yes. 200 and?
And you can even buy the
both ways. You can now find, at the end, you can find both. So the first thing we did is we completed the table. After completing the table, please read the question, part A. Yes, answer it now. 50 over 500. 50 over 500. 10%. So the first question says that if a student is selected randomly, what is the probability that he or she is from business department? So let's go by definition. By definition, probability of any event, first you have to define an event A. Define event A that the selected student is from business. So a complement will be that the student is not from business. And in this example, the only category which is not from business is engineering. So engineering becomes a complement. Similarly, we define other events. We define a student from the mom. If the selected student is from the mom, we call this event to be B1, then B2, and then B3. Why I did not write here B1 complement? There are more than 2 events. So B1 complement is actually B2 and B3 combined. So I cannot write any one of those as complement. So let us go to the solution. The first thing we need to do is we filled the table. The green elements were already given in the question. The red ones are the ones that we filled. After filling the table, we need to go back to the definition of probability. The definition of probability is N of A divided by N of S. I need these two numbers to get the probability. How many outcomes in the experiment are favorable to your event A? That the student is business. 50, good. And how many outcomes in your space? 500. So the answer will be 10%. Next question. What is the probability that the student is not from business? Here you can solve it directly also. The student is not from business. You can solve it directly as probability of this event is the number of outcomes in this event divided by N of S. So the number of students not from business is 450 and 500. You can solve it directly. But imagine if I don't give you the number and I give you the probability of business and ask you the probability of not business, you will be forced to use the complement rule, right? So using the complement rule, this probability will come out to be, we have probability of A already with us. So probability of A complement will be 1 minus probability of A, which is 1 minus 10%, which is 90%. What is the probability that the selected student is from Riyadh? Simple application. The number of students from Riyadh divided by the total number of students, which is 100 divided by 500. This is 20%. Yes.
Is this the easiest chapter we have in this course?
No. This is the toughest chapter in this course. Wait for the next concept.
Yeah.
We are trapping you into the course. Once you start feeling easy, then we will throw the difficult questions. What is the probability that the selected student does not belong to Riyadh? Complement rule. You have 20% as the probability for Riyadh, so not Riyadh will be 80%. What is the probability that the student is from business? Now, look here. I will, is from business. This is one of the events. And then there is a very, very, very important and. He or she belongs to Riyadh. What is this event from business? This event, we gave it notation A. What is this event? We gave it B2. And what does A and mean? Intersection. Remember, in any question, and corresponds to intersection or corresponds to union. So we are required to find probability of A intersection B2. Now here I will not use any rule. I will simply find this probability to be N of A intersection B2 over N of S. So go to the table and see how many outcomes belong to A intersection B2. Let me highlight this one with green color. N of A intersection B2 with the green color. And in the table, where is N of A intersection B2? Here is N of intersection B2. Okay, 15. So you put it into the formation, 15 by 500, 3% is your final answer. Next question. What is the probability that, now see the difference between part E and part F. It's the same question, but without and, now with or. What is the probability that the selected student is from business or from Riyadh? What is the probability that the student is either from business or from Riyadh? So now the same two events, but we need union probability. To get the union probability, we make use of the addition theorem. The addition theorem says what? Probability of A union B2 is equal to probability of A at the bottom. Let me bring it at the top. Probability of A plus probability of B2 minus probability of A intersection B2. In previous three questions, we already found probability of A. We already have B2. We already have A intersection B2. So it's just a plug-in. Next question says, what is the probability that the student is from business department, but not from Riyadh? Highlight this is an important question. Highlight the information. The student is from business department. What is business department? No, notation. A. But from, what is from Riyadh? What is not from Riyadh? And here but means and or. You want both conditions to be satisfied or you want either of them to be satisfied? Both. So here but means and. So here you require A intersection B2 complement. The common area between A and B2. What is the common area between A and B2? Suppose this is A, this is B2. I will highlight A with yellow color. Okay, you see it? I will highlight B complement with the blue color, everything outside B. This is so big. B complement with the blue color, and the intersection will turn into which color? green. So try to see where does it become green. Where does it become green? It's actually A minus A intersection B. It's actually the part of A excluding the intersection part, excluding the yellow part. So this rule says that probability, this rule is exemplified here. Probability of A intersection B complement is the part of A excluding A intersection B. It's the part of A excluding A intersection B. Once you know the rule, it's just a plug-in. You already have probability of A, you already have probability of A intersection B2. Are A and B2 mutually exclusive? Are A and B2 mutually exclusive? Why? Yes. What was the definition of mutually exclusive? There is nothing common. The intersection should be phi, or the probability of intersection should be 0. Is this true for this example? What is the intersection between A and B2? There are 15 students which are falling on the intersection. So it is not a null set. The probability of the intersection is not 0. So as a result, you will say no, because the probability of A intersection B2 is not equal to 0. They are not mutually exclusive. What is the probability that the student is neither from business nor from Riyadh? Important. Not from business, not from Riyadh. What does this nor mean? And or? You want both to satisfy or either one to satisfy? Both. This nor means and here. So this nor will translate to intersection here. So you want A complement intersection, B complement. De Morgan's law. De Morgan's law says A complement intersection B complement is A union B whole complement. Then complement law. Complement law says that the probability of complement of an event is equal to 1 minus the probability of original event. And this one, you already found it in one of the questions. Yes, simply plug in. So first I applied from this step. From this step, I applied the De Morgan's law. It became A union B whole complement. Then I applied the complement law. It became 1 minus A union B. And then I already have A union B to be 135 over 500. Plug in, and the final answer is 73%. Any questions up to this point? This example was a brief demonstration of those 3 or 4 concepts that we studied: the complement rule, the mutually exclusiveness, the exhaustiveness, the De Morgan's law, the addition theorem, intersection, union. All of those were demonstrated here. But this is a demonstration. This is not a real example. When the real example comes, it will be tough the toughest part of chapter 2 is to extract the information in terms of events and getting to know what is required. Once you extract the information that probability of A is this, probability of B is this, A intersection B is this, and I'm required to find A union B, it's simply a plug-in from formula sheet. You just have to plug in the answers and that's it. So the difficult part is to read the question, define the events, and getting to know what is required. That's the most difficult part for every probability question. Any questions? Let us move on to the next topic. Next topic is the conditional probability. Sometimes we are interested to know the probability of an event where we already know that another event has already happened. Let me give you an example. What are the chances that if I select a student from this class, the student will not be able to read this font size? This is one question. Okay, and I ask you to give me the answer and you give me a specific probability. Okay, I define event A that I will select one student randomly from this class. Okay, and I will ask this student to tell me if the student is able to read this font size. Okay, then I give you some extra information and I tell you that the student is wearing glasses. Now find the probability that the student will be able to read or not. Or I give you an extra information that the student is sitting in the first row. Will this extra information help you guessing the answer? In the first case, probably no, but in the second case, when I tell you the student is sitting in the first row, it will help you. Or I tell you the student is sitting in the last row, you will downgrade your guess. The probability you will downgrade. If I tell you the student in the first row, then you will push the answer upwards. So sometimes before finding any probability, we have some additional information. This additional information is in terms of an event. For example, event A is that the student is sitting in the first row. Event B is that the student will be able to read the font. And I tell you that event A has already happened. The student is sitting in the first row somehow. Now find the probability that the student will be able to read it. Now, will your answer or your guess without this information, whatever was your guess, will you change your guess? If I give you additional information, yes. This is what we call conditional probability. Probability of an event conditional to another event. For example, here in this question, I ask you, what is the probability that if I select a student randomly, the student is from Riyadh? What is your answer? 100 over 500, right? What if I tell you that the student is from business? I already tell you he is from business. Now tell me, what is the probability that the student is from Riyadh? Now you focus here. Here, 15 over 50. So your answer will change. Now your sample space will change because I told you that you are in the first column. You don't have to look for the whole. You only have to look for the first column. So if I tell you the student is sitting in the first row, now you have to see out of the first row, how many are able to read that font size. So the answer will be the number of students able to read that font size from the first row divided by the number of students in the first row, not in the whole class, right? So let's go back and read the form. Sometimes we are interested in finding the probability of an event A conditional to another event B. Conditional means we know that B has already happened. Okay, this kind of probability is called conditional probability. It is denoted by A given B. Now remember, A given B is different from A divided by B. This is not a slash. This is a slash. It has a different meaning. This is given. This is what we will use in this course. A conditional B, A given B. It's the second one, not the first one. This is completely different. Yes. And conditional. What is the probability that I select a student and the student is sitting in the first row and is also able to read the font? No. That must happen. In the conditional, I'm telling you the first one has happened. I'm asking you to find the probability of the second one. So for the conditional, I'm telling you one of them has happened. And for the intersection, in the previous question, I was asking you for the intersection. I'm asking you the student belongs to Riyadh and the student is from business. Now I'm telling you the student is business and asking you for Riyadh, right? It is denoted by A given B. And there are two ways of finding conditional probability. One of the way is to find the probability from the reduced sample space, the way we just looked at it into the table. Some of the examples you will not be given the sample space. So the second way of finding the conditional probability is through the formula. Now I will demonstrate to you both ways. The way I will design the example, both ways will be possible. But the way the question will come in exam, one way will be possible, either from the reduced sample space method or from the formula method. Now the formula says that the probability of A conditional B is equal to A intersection B divided by probability of B. Similarly, if I tell you that the student is able to read, what is the probability that the student is sitting in the first row? B given A. So probability of B given A is also A intersection B divided by probability of A. Now have a look at these two equations very closely. This one and this one. And solve these two equations for A intersection B. What do you get? From the first equation, what is probability of A intersection B? And from the second equation, look at the difference between the two of them. Both of them are intersection probabilities. What is the difference between the two of them? Now you will get your answer. Here in this equation, you're trying to find the probability that A will happen and B will happen. On the left side, A intersection B. On the right side, you have the probability of B has happened first, multiplied by the probability that A will happen given B has already happened. So in the first formula, A is dependent upon B. So first B happened, and you know B happened, and then you're trying to find the probability of A. In this one, B is dependent upon A. So first A happened, you have the probability of A, and then multiplied by probability of B given A. If you solve the two of them, this is what you get. And moreover, what if I ask you find the probability that the student will be able to read this font size given I took tea in the morning today? Find the probability that the student will be able to read the font size on the screen given I took tea in the morning. If the conditional event has nothing to do with the event that you are finding the probability for, the conditional probability will be simply equal to unconditional probability. The conditional event will not help at all. It will not change the probability. So it will simply be the number of students who are able to read divided by the total number of students, because this extra information that I'm giving you that I took tea in the morning, it's independent. If the two events are independent, then the conditional probability is simply the unconditional probability. And if you plug this guy and this guy in these two equations, what do you get? In case A and B are independent, this will be this will be this. What will happen to the intersection? It will become the product. It will become the product, right? So if I ask you to find the probability that a student will be able to read the font size and I took tea in the morning, what will be the answer? Find the two probabilities separately. Find the probability that student is able to read the font. Find the probability that I took tea in the morning and just multiply the two of them, if they are independent of each other. If they are not independent, apply these rules. If they are not independent, apply these rules. Okay, so let us move forward. And I think I have already covered this slide in my last few sentences. A multiplication rule. if you solve A intersection B from those two formulas, you will get 1 and 2. These two formulas, both of them are correct, but it depends, either A is dependent upon B or B is dependent upon A. So both of them are correct. And then inside these formulas, if A and B are independent, B given A will be simply B. A given B will be simply A. And when you plug them in, A intersection B becomes the product, simply the product. Okay. Let us quickly have a flavor of the question. Read part A. It's the same data. Read part A. If a student is selected and is found to be from the business department, what is the probability that he or she belongs to Riyadh? Found to be from the business department. So conditional event comes at the end. Given, after given sign, right? What is the given information comes at the end. What is required comes in the beginning. So I'm required to find the business or I'm required to find Riyadh? Riyadh. So Riyadh comes first. This is required. You are required to find the probability of B2 given the information about A. Apply the formula. What is the probability of B2 given A? Intersection divided by A, which is equal to, you found these two probabilities separately. 15 by 500 divided by 50 over 500, which is, use the revised sample space method. Instead of formula, use the revised sample space method. What was the given information? What was the given information? From business. So reduce your sample space to this one. According to the given information, make this your sample space. Out of this sample space, find the probability of B2. That will be 15 by 50. So if you reduce the sample space with respect to A and then find the probability of B2, that will be probability of B2 given A, which is again directly 15 by 50. What I'm trying to explain to you is that the way we will give you a question in exam, both of the methods will not be applicable. One of them will be applicable. Either the reduced sample space method will be applicable or the formula will be applicable. But they will both give you the same answer. Okay, we will continue with the conditional probability in the next class on Sunday, inshallah. I will try my